Number 5 in free response here was a variation here on area and volume problem. So let's see what's going on. They've given you two functions right here. We've got the graphs of g of x, which is the square root of x. That's this one up here. So square root of x, y equals on top of that. So that's g. And then on the bottom right here, we've got h of x, which is x over 3. That is a linear function, so it looks something like that. All right, first question right here. For part A, find the region of the area of region R. So area here is just going to be our integral of top curve minus bottom curve. So we've got the square root of x on top minus x over 3 on bottom. We're taking that integral with respect to x, and the limits of integration are actually given to us. You can tell right here that these curves intersect at x equals 0, and then again right here at x equals 9. So our limits of integration are 0 and 9, and I think this part should be pretty straightforward. Anti-differentiating an x to the 1/2 is going to become an x to the 3/2. We'll divide by that exponent there to get 2/3 out in front. And then minus, remember everybody, this is a 1/3 x cubed, so that'll become an x squared. Dividing by 2, that should be an x squared over 6, or a 1/6 x cubed, however you want to do it. And we're going to evaluate all of that from 0 to 9. So let's see what happens here. Let's put the 9 in first. And what we've got to do, this has given you guys some trouble this year, taking 9 to the 3/2 power. So remember everybody, what that means is we're going to take the square root of 9, and a mistake that I see a lot of people making, it's not really a mistake, is they want to cube the 9 before they take the square root. Now remember, this is a non-calculator question. Now you could probably do some multiplication and figure out that 9 cubed, I believe, is 729, but then taking the square root of 729 by hand is probably something you guys are not going to be able to do. So what we really should have realized, though, is that you can take the square root of 9 first and then cube the result. That just becomes 3 cubed, which is going to be 27. That's where a lot of people ran into trouble on this problem. But that still needs to get multiplied by a 2/3. So it's a 2/3 times that 27 right there, minus 9 squared is going to be an 81 over 6. Now that's what happens when we put the 9 in there, but we should also consider what happens when you put the 0 in there. But this is a polynomial function. All of that is just going to get you 0. So this got a little bit messy from here, everybody. Let me pick this up right over here because I think I'm going to need the space. And let's see what it looks like. 2/3 of 27 is going to be an 18, and then minus the 81 over 6. As soon as I saw that, I realized both those numbers are divisible by 3, and that got me a 27 over 2. A couple ways you could go from here, but 27 over 2 isn't that hard to figure out, is 13.5, and 18 minus 13.5 is going to get you 4.5. I believe in the answers they gave us, they had 9 over 2, but of course both of those answers are going to get you full credit. Okay, so there's the area of region R in part A. Let's move on to part B now. Right, here you go, but do not evaluate. That's something you want to circle as soon as you read it, guys, because that means the integral we're about to set up is probably too complicated to do by hand, or just really, really time consuming. And if you miss that important detail in the directions, you can waste a lot of time here trying to come up with an answer that they're not even looking for. So write but do not evaluate an expression involving one or more integrals that gives the volume of the solid generated when R is revolved about the horizontal line y equals 4. So it might just be faster for me here, guys, to just draw a quick sketch of this region again. So we had this linear function here, we had a square root function that looked something like that, and they intersected right here at x was equal to 9 and where y was equal to 3, if I'm not mistaken. Now, y equals 4 is going to be that line right up there. So here is our axis of revolution. That means, everybody, that this region is being spun about a horizontal line like that. And as we studied a lot back in chapter 6, that means that this is going to be a dx problem. Good to know. But what makes this problem kind of challenging and interesting is the fact that we've got all of this space right here in between region R and the axis of revolution. Our region is not flush up against R, which means we're going to be dealing with washers here. A major radius, capital R, and a smaller radius, little r. So major R always starts at the axis of revolution, and in this case I'm going down through the first curve and into the second. So what I just drew there in green is major R. Let me go ahead, I kind of skipped a step here already, but I'll come back to it. Major R is going to be top curve minus bottom curve, and the top curve here is y equals 4. Minus the lower curve right here, which was y equals x over 3. That'd be the linear function. Little r then also starts at the axis of revolution, goes down to hit the curve, but stops when it hits the first one. So that would be little r right there. Top curve is still 4 minus the bottom curve, which is the square root of x. Now, what I skipped just a moment ago that I probably should have written, we're doing washers here for our cross section, and the formula for area of a washer is one we should have memorized: pi times capital R squared minus lowercase r squared. So back to where I was in blue here, area written as a function of x is going to be pi times, and these ones aren't too terrible, so I'm going to go ahead and write them out. Capital R is 4 minus x over 3, and we're going to square that, minus lowercase r, which is 4 minus the square root of x, and we will square that. Okay, so that's your a of x function right there, and now they want us to set up, but not evaluate, an integral that's going to get us the volume of this region. So volume is going to equal a definite integral. We said a long time ago it would be taken with respect to x, so I'll put that dx right there, and we've said this repeatedly throughout the course of the semester, guys. Whatever you come up with for your a of x function, that's your integrand. Now, since I'm interested in getting this answer as quickly and easily as possible, and because I have very clearly labeled what my a of x function is, all I need to do is write a of x right there, and the AP grader will look at this and say, okay, as long as this person labeled what a of x was, we know that that goes here. Nice and easy. All I'm missing are limits of integration, which need to be my lowest and highest values of x, and just like in the area problem of a, we're starting here at 0, and we're ending right here when x is 9. So that's my integral right there, guys, which I set up, but I do not have to evaluate in order to come up with the volume of that region when it's revolved about the line y equals 4. Okay, so that's part B. Let's take a look at what's going on with C here. Now in this one, I think a lot of people got bothered by this problem just because it didn't sound like something you've ever been asked to do before. And I've got to warn you guys, the AP test writers are going to do that to you on purpose. Most of what you're going to see on the test you will have seen before, but once in a while they throw something unique at you just to see if you can think outside of the box. So we've got this region here, and they want to know, find the maximum vertical distance between the graph of G and the graph of H in between. And guys, I'll be honest with you, I missed this problem when I did it the first time because I neglected this interesting little detail right here. We're going all the way to x equals 16. And when I did this problem the first time, I just considered it going from 0 to 9, but actually that means I drew this kind of poorly. I should have extended this graph a little bit further over to the right now, in which case the linear function just keeps going at the same rate, and the horizontal function kind of does something like this. So that made this problem interesting here, guys. We had to go all the way to 16 with this one and try to find the maximum vertical distance between these two graphs. Okay, two things to realize. Number one, first and foremost, this is a maximum problem. And where can a maximum value of a function occur? Two possible places: critical points and endpoints. Now, the endpoints are given to you right here, 0 and 16. Critical points, though, come from where the derivative of a function is either equal to 0 or undefined. Well, the derivative of what? That's what was odd about this function. What we need to do, guys, is come up with a function. We're going to make this ourselves that measures the vertical distance between these two curves. So I'm going to go ahead and call that piece right here D, and we've got to come up with a way of figuring out what D is? Well, this is actually the exact same concept we were using right back over here in part A when we were measuring the height of all of our rectangles right here. And this quantity right here was equal to whatever that distance was. It's top curve minus bottom curve. So over here, I'd be tempted to do the exact same thing. The only problem is this. The way I've drawn d right here, it's the square root function on top and then the linear function on bottom. But if we go all the way out to x equals 16, now all of a sudden those things flip around a little bit. Now it's linear function on top, square root function on the bottom. The way I'm going to get around that is just do one or the other. I'm going to go with what I had initially, which was the square root of x, and then minus the linear function, which was x over 3. And really what we want is the absolute value of that function over here. When you put absolute value around a subtraction expression, it doesn't matter what order you're subtracting those two things in. So that's the function. Now, we're actually going to kind of ignore that absolute value on the next step. So d prime, I guess I should call this d prime of x, everybody, would be, let me ignore the absolute value right now, the derivative of the square root of x is going to be 1 over 2 root x, hopefully you have that memorized by now, minus the derivative of x over 3, which is 1/3 x, that derivative is just going to be 1/3. So there's the derivative of this function. We're going to set this thing equal to 0 and solve. I'll bring that 1/3 to the other side and get a 1 over 2 root x is equal to 1/3. And now here's a trick that some people forget you're able to do. I've got an equation with fractions on both sides. Let's just reciprocate both sides. 2 root x has to equal 3. Okay, so then the square root of x is going to equal 3 over 2, and x then comes from squaring both that numerator and denominator, and we get 9/4 for the only value of x for which this derivative would equal 0. Now, if you're wondering why I was able to ignore the absolute value, guys, remember then that the absolute value just means that the expression could be this, or we could reverse the order. X over 3 minus the square root of x. And if we set that equal to 0, we just end up in one step right where we were right here, and we'd get the exact same value again. So this is the only critical point of this function here, everybody. X is equal to 9 over 4. So now, where are we? I'm going to switch colors on you here, guys. We have identified our two endpoints of this interval, 0 and 16, and our one and only critical point here. So what we need to do now is evaluate this d function here at 0. We need to evaluate d at the critical point of 9/4, and we need to evaluate d at the right endpoint, which is 16. That was supposed to be a parenthesis. Okay, so come on. There we go. All right, let's get working on this then, guys. D of 0, well, this is a fun one. Right here, where the two curves intersect, the vertical distance between them is 0. I think I can spot that one pretty easily. By the way, the exact same thing would have happened right here at 9. The vertical distance between them doesn't exist, so it's 0. But at 9/4, everybody, which is probably a little bit to the right of where, that's only, 2 1/4, so it's to the right of where I have d drawn right now. Let's work on that. And quite simply, we're just following this function right here. At 9/4, we're going to do the square root of 9/4, which is going to be 3, it's going to be 3 over 2. Gotcha. And then minus, we have 9/4 divided by 3. That's going to be a 3/4. And we're doing the absolute value of that. I don't think that's really going to be important in this problem right here, but it might be, so it doesn't hurt to write that out. Okay, so that becomes what then, guys? This is now 6/4, if I wanted to look at it that way. 6 over 4 minus 3 over 4. The vertical distance between those two curves at the spot where d is equal to 9/4 is 3/4. This was the answer that I wrote down when I did this problem the first time, time. And a few of you guys got that same answer. So if you did, just like me, you were thinking some good thoughts on that problem and doing some good work, you just ignored what was kind of a sneaky underhanded trick that they changed the interval on us here. But hey, lesson learned, you've got to read the directions. So now let's do d of 16. So putting a 16 right in here, this will get us the absolute value of the square root of 16 is 4, and then minus x is 16 over 3, and nothing happens right there. This 4 becomes 12 over 3, and 12 over 3 minus 16 over 3 is negative 4 over 3, the absolute value of which is positive 4/3. And so, guys, we've considered this d function, this vertical distance function, at all 3 points that we needed to. The 2 endpoints, here, and then also at its one critical point. We were looking for the maximum possible distance between them, so what we found right here is that max distance right there, so the max vertical distance is equal to, didn't leave myself much room there, 4/3. So that was a pretty tricky problem there for part C, but that's everything you needed to do in order to get all 3 points on that problem.